Now we want to take a look at the graph of the derivative function and see what that tells us about the original functions increasing and decreasing. So notice this does say f prime. So the values on this graph, the y values, are derivative values. And derivatives are slopes of tangent lines. So if I first think about a horizontal tangent line where the slope is equal to 0, that would be all the points here along the x-axis. So this would be where f prime of x is equal to 0, or we could say the graph lies on the x-axis. Okay. And to look at that, we'd have a point at about here, here, and here. Those are points that lie on the x-axis. The slope is equal to 0. Slope of tangent equals 0. So those are the points that we're interested in. When the derivative is equal to 0, remember, we have horizontal tangent lines. That divides up the rest of the slope into either positive values or negative values. So let's think about if the slope is positive, the derivative is positive, slope greater than 0, f prime of x greater than 0. That's these numbers up here. Positive numbers are above the x-axis. So that gives us this portion of the derivative graph. Here, we would have slope less than 0 because the derivative is less than 0, and those are below the x-axis. So at the graph that we're looking at, we have our derivative in terms of positive numbers, negative numbers, or zeros. So think of the derivative in terms of numbers. Derivative as numbers. Okay. Now, we have the derivative equal to 0, but there is another place where the derivative changes. The derivative changes at 0, positive, negative, 0, above and below. We also have f prime of x does not exist. Now, we haven't really looked at that, but when the derivative does not exist, that would be, say, at a vertical asymptote. So that would also be a place where the graph changes, not just at 0 where it goes from above to below, but where it changes. So when the derivative does not exist, that's something we may also need to look at, but it does not apply to this particular graph. So we're supposed to be talking about what does all this have to do with increasing and decreasing functions? Well, if a function is rising, okay, if f increases, f prime is positive. Slopes are positive, slopes of the tangent line. If f decreases, f prime is negative. So information about our slopes tells us about the graph. The slopes are the derivatives. So the derivatives tell us increasing and decreasing. Let's see if we can look at those derivatives as the numbers and give us the function as words. Let's look at my function, f. Now here I have above the x-axis less than about negative 1.8. Above the x-axis, positive slope, function increases. So on this part of the graph, I would have f increasing. And on this part of the graph, I would have f increasing. And all these numbers down here are less than 0, so this would be where f decreases, all the way between those numbers. So my function f, let me make that a capital so it matches what I'm saying up there, between about negative 1.8, my function is increasing to the left of that. And I don't know where, but it increases. Decreases to the right of that all the way till I get to a positive 1 point something. We'll say 1.8 because it probably should be about the same. Decreases to there. Whoops, I missed it. And then increases again. Now this would be the graph of f. I didn't put any numbers in. It could be here on the axis. My x-axis could be up here. I don't know where it is because I only have a graph and I can estimate where the graph of f lies. It increases to a certain point and then decreases and then increases. And these values here mean there may be some different little shapes in the middle, but this is all I have for increasing and decreasing. This is the graph of f. I want to draw vertical. Now, once we look at the graph of f, increase, decrease, increase, let's go totally different and think about the graph of f double prime. Now this is the graph of f prime. F double prime is the derivative of f prime. So let's think back when we looked originally at the graph of the original function that gave us f prime. This function increases, so the derivative is positive. This function decreases, the derivative is negative, and then it increased, so the derivative was positive again. Let's think about the derivative of this function. This function is decreasing all the way to negative 1. Its derivative has negative slopes there. So its derivative, f double prime, lies below the x-axis there. This function increases to 0. Its derivative is positive, and then it decreases. Oops, going too far here. At 0, it changes to decreasing, so it has to go down. And then it decreases to there, below the axis, to 1. I'm losing my 1. 1. So it's below the axis till I get to 1, and then it increases, so it's above the axis again. So f double prime is the derivative of f prime, where the f prime decreases to negative 1. This one is below the axis. Where it increases to 0, it's above the axis. It decreases, the derivative is below the axis. It increases, the derivative is above the axis. So you can do all kinds of information about f, f prime, and f double prime if you consider the slopes being positive and negative and relating that to the increasing and decreasing of the function. It takes practice. In this section, we're going to look at the first derivative formula and how that relates to increasing and decreasing functions and relative extrema. So let's look at the formula f of x equals x cubed minus 6x squared plus 1. And we need to look at the first derivative. F prime of x is equal to 3x squared minus 12x. Now when we look at the first derivative, that is the slope of a tangent line, we think about where it's equal to 0, where it's positive, where it's negative, where it does not exist. This is a polynomial function. The derivative is a polynomial. There is not any does not exist. So we want to think about where the derivative is 0, because that's where it changes from positive to negative and negative to positive. So let's first take this derivative equal to 0. Now if I set it equal to 0, I want to know every possible x where it equals 0, so I need to factor. I can pull out a 3x, and I'm left with x minus 4. Since this is 3x times x minus 4 equal to 0, I let each piece equal 0. For 3x equal to 0, I have x equal to 0. For x minus 4 equal to 0, I have x equal to 4. So at x equal to 0 and at x equal to 4, my first derivative is 0. That means those are the possible changes in the graph, because that's where the derivatives equal 0. One of the easiest ways to work with these points and our pluses and minuses for slope to yield increase decrease is to put them on a number line. Now it's not really the x-axis, it's just a number line. And I know that at those 2 points, my derivative is equal to 0. But I want to know increase and decrease, so I need to know where they're positive and where they're negative. There are a lot of different ways to write this. What I want to do is look at each individual interval, and I have 3 here, and look at a single point in the derivative on each interval. Whatever the derivative does at that one point is what the derivative does on the whole interval. So let's first look here for everything less than 0. So I'm on this interval, which is from negative infinity to 0. And I want to pick one number in there and plug it into my derivative. Now, what I'm going to plug into is the derivative in factored form. So I'm going to change my 0 here, since I've already found my 2 points, and just call it f prime. And that's where I'm going to plug in my numbers. Pick anything less than 0, say negative 1. If I put a negative 1 in here, f prime of negative 1, 3 times negative 1 is a negative 3. It's a negative number. Negative 1 minus 4 is negative 5. That's a negative number. If I multiply a negative times a negative, that gives me a positive number. So on this first interval, I have a positive derivative. You can make notes. My derivative, I got a negative and a negative, which made it positive. And that is the derivative. The number for the derivative is positive. Pick a number, a test value on the next interval. This is the interval from 0 to 4. Let's pick 1. F prime at positive 1. 3 times 1 is 1. 1 minus 4 is negative 3. That's a negative. A positive times a negative is a negative. I could just write it in there if I wanted to. Plug in my 1 and I get a positive. Plug in my 1 here, I get a negative. Multiply, the derivative is negative. One more interval. Here, the interval from 4 to infinity. Pick any number. Let's do 5. 3 times 5 is 15, which is positive. 5 minus 4 is positive. Multiply 2 positives together, you get a positive. So over here, each factor was positive, multiplied to give me a positive. So you can, with enough practice, leave out a lot of the writing and just think about what happens on each interval with your little symbols to tell you what the derivative does. So now we have to think back. If the derivative is a positive number, derivative is positive, the slopes are positive, my function f increases. Whenever the derivative is positive, the function increases. It increases over here on this interval because the derivative is positive, and it decreases in the middle because the derivative is negative. So what does the function look like? It looks like it increases to 0, decreases to 4, and increases again. So that's what the general shape of the function is: increase, decrease, increase. Now, because of the shape of the function, look at this function. This tells us something about our relative extrema. At 0, where I had my high point, it increased on one side, decreased on the other side. That means here at this point 0, I have a relative maximum because it increased and then decreased. And at 4, where it decreased and then increased, I have a relative minimum right down here. Relative min at x equal to 4, relative max at x equal to 0. Now, I could actually plug numbers in and find the actual function value. A maximum at x equal to 0, I plug in 0 for x into the function, and I find my value is 1. That's the maximum value of the function at that point. Now, we've seen the way the function continues to increase, so it's not absolutely the highest. The same thing with the min. I could plug in 4 for x and find a value when x is equal to 4, and that would be the minimum. And I could just plot a few more points and get a general idea of where the graph lies. But this is enough to give me an idea of the shape, just not exactly where it lies on the graph. We're going to look at another formula for the first derivative and see how we can determine increase and decrease. And notice, this is already the first derivative. We don't have to take the derivative. We've been given the first derivative. So we think slopes equal to 0, slopes positive, slopes negative. So that would be the derivative equal to 0. And then from that, we'll find our points. Whenever x's, we'll make the first derivative equal to 0. These two are multiplied together. Only the x plus 1 is squared. So let's set each piece equal to 0 and see what the x's are. Well, here it's pretty clear x is 2. This one, we have x plus 1 squared equal to 0. But that's not a complicated process. You take the square root of this side and get x plus 1. Square root of 0 is 0. So we have x equal to negative 1. So we have two numbers where the derivative is 0. If everything were multiplied out, this would be polynomials. So we have no places where the derivative is non-existent. This is all we have to deal with. And these are the two places where the derivative changes sign. So let's set up a number line. Negative 1 and 2. And notice when I set this up, I don't put all my points in. I don't plug in 0 or other numbers. I don't call it the x-axis. This is just a number line that helps me organize my derivatives. At these 2 points, the derivative equals 0. And I want to go back now and determine the sign of the derivative on the sides of those points. So let's say between negative infinity and negative 1, let's look at the derivative. Say f prime at negative 2. Negative 2 minus 2 is negative. Negative 2 plus 1 is negative 1. Squared is positive. I multiply a negative times a positive, I get a negative. So my derivative at, not at, but less than negative 1 is a negative number. The next interval from negative 1 to 2, I can pick 0 here. That's a good one. f prime at 0, back up to f prime. 0 minus 2 is negative. 0 plus 1 is positive. Squared is positive. Negative times a positive is a negative. My derivative is negative again. At negative 1, I had a place where the derivative could change. Possible places for it to change. But here, the derivative sign did not change. Well, let's look at the next interval from 2 to infinity. F prime at 3. 3 minus 2 is positive. 3 plus 1 is positive. Squared, still positive. So here, my derivative is positive. And these are just numbers that I picked. I could pick negative 10 in this interval. I could pick 1, 1/2. Over here, I could have picked 3 or 5 or 7. Whatever number you want within that interval means the derivative has that sign on the whole interval. So now that we've got our derivative signs, we need to go back and look at the plus and the function values for increasing and decreasing. So f, when the derivative is negative, f decreases. When the derivative is negative, f decreases. When the derivative is positive, the function increases. So this tells me about what the function is going to look like, just not the specific places on a coordinate system. My function decreases to negative 1, decreases again to 2, and then turn and increases. So this is sort of a general idea of what my function looks like. Something must happen here, maybe a little flat area because the derivative is 0 here. So more than likely in this spot, it goes down, has a little bit of a flat area before it decreases again. Since the derivative is equal to 0, lies on the axis here, something happens. Okay? Now, how does that relate to our relative extrema? Well, I'm decreasing and decreasing all down here, and then it turns to increase. So at this point, since it changes, and this is the low point, I have a relative min at x equal to 2. It's a relative minimum. I do not have a relative maximum. So there is no relative max. The example that we want to look at for our absolute extrema is the function f of x equals x cubed over 3 minus x minus 2/3 only on the interval from negative 2 to 2. So we don't want the whole function, we just need negative 2 to 2. So we have to find out where the relative or local extrema are so that if there's a high or low point within the interval, we know that's where they occur. So we need the first derivative. So f prime of x is equal to, the derivative of x cubed is 3x squared, keep the 3 in the bottom, minus the derivative of x is 1, and the derivative of 2/3 is 0. So I can cancel my 3 over 3, and my first derivative is x squared minus 1. So I can either factor that, which and set it equal to 0, x minus 1, x plus 1, or you may be able to just look at this and know that x could be plus or minus 1. Either way, if you set it equal to 0, we have our x equal to 1, and then we have x equal to negative 1. So we have a possible max or min at those two values. Relative extrema, max or min. But we also have to test endpoints. So we have to go back now and test every value in the function. Not the derivative, but the original function. Because we want to find out at x equal to negative 2, x equal to 2, x equal to 1, and x equal to negative 1, what are the y values? When I go to graph, I need to know what's the highest and lowest. So f of negative 2 would be negative 2 cubed over 3 minus negative 2 minus 2/3. You do all your algebra here. This would be a negative 8/3 minus 2/3 would give me negative 10/3, which is 3 1/3 plus 2 gives me a negative 1 1/3 or negative 1.33, and the 3 goes forever. I check f of 2. I have 2 cubed, which is 8/3, plus, minus 2 minus 2/3. 8/3 minus 2/3 is 6/3, which is 2 minus 2 gives me 0. F of 1 would be 1/3 minus 1 minus 2/3. That's a 2. Whoops. Okay. 1/3 minus 1 is negative 2/3. Minus 2/3 is a negative 4/3. Negative 4/3 is negative 1 1/3. And f of negative 1 would be the negative 1 cubed gives me negative 1/3 minus negative 1 minus 2/3. And so 1/3, negative 1/3, negative 2/3 gives me negative 3/3 plus 1 gives me 0. So when I'm looking at the absolute extrema, it depends on if you're asked about absolute maximum or absolute minimum. If you think about these, think about it on a graph. If we're only looking between negative 2 and 2, then at f of 2, I'm at 0. At f of negative 1, I'm at 0. And then at negative 2 and positive 1, I have values of negative 1 1/3. Positive 1 is negative 1 1/3. Negative 2 at negative 1 1/3. And so it looks like my graph goes up and then down and then back up, and that's where I'm limited. That is the end of my function. The highest value, the maximum value, would be y equal to 0, because that's the highest point at 0. If you were asked for the minimum value, that would be y equal to negative, I'll say negative 4/3 to be exact. And these are the absolute or global max and min for that function. When we looked at concavity before on the graph of a function, we talked about the words concave up and down based on the way the slopes of the tangent lines changed, the rates of change. So let's look back first at a graph. This is some original function f. And let's think for a minute about this function. It looks like it's concave up. So what does that have to do with the slopes or the first derivative values, rates of change? The slope of the tangent line here would be a big negative number. Slope of the tangent line here is not quite so big. Slope here would be 0. So far we're going from a large negative number to a small negative number to 0. As we move over here, we get a small positive, and up here we have a big positive number. So what we have on this graph is that as we move from left to right, the slopes increase. Or we could say f prime increases. And that shows us where the function f is concave up. If we have a function that's concave down, the exact opposite happens with the slopes. For concave down, we would have that the slopes decrease, or f prime decreases, which means f would be concave down. So the first derivative decreasing or increasing makes a difference in how the function is concave down or concave up. So let's look at this graph of the first derivative and find out about increase and decrease. Start on the left. As I go here, the function all the way down to this point is decreasing. And then from here up to here, it's increasing. From here down to here, it's turned around, it's decreasing again. And then from this point on up, it's increasing. So we're looking at the graph of the first derivative, thinking about it not above and below the axis, but whether the first derivative graph is increasing or decreasing. And if the first derivative increases, the function is concave up. So let's think now about the original function. So if I'm talking now about the function f, let's think about it on a line. Let's suppose that this point is negative 0.5. And this one is supposed to be about the same, would be positive 0.5. And of course, right here we have 0. So on this number line, if I put negative 0.5, 0, and positive 0.5, the function is concave down because f prime decreases to the left of negative 0.5, concave down. Between negative 0.5 and 0, the derivative is increasing. The original function then is concave up. Where the derivative decreases, the original function is concave down. And finally, where it increases on the end, the original function would be concave up. So that we have concavity that we can look at based on the first derivative. Because we can do concavity, we can also talk about points of inflection. Points of inflection occur where concavity changes. And so we have concavity changing at our points changing at negative 0.5 from down to up, from up to down at 0, and from down to up at 0.5. So the points of inflection for this are at x equal negative 0.5, 0, and positive 0.5. So we can tell concavity from the first derivative.